Okay. Okay. Okay.
All right, hello everyone. Welcome back to another Quantum Matters seminar. It's my pleasure today to give you Hitesh Changlani from the Magnet Lab in Tallahassee, who's going to tell us a little bit about material-specific model Hamiltonians. Thank you, Hitesh, for joining us today. And
Yeah. Okay, thank you so much, Adrian, for the invitation. And I do have a slight technical issue. I cannot see questions from the audience. So, Adrian, if there are any questions, yeah, just feel free to interrupt me. And yeah.
Good.
Okay. I'd like to just first acknowledge my funding sources. I am supported by the National Science Foundation. As Adrian mentioned, I am an assistant professor at Florida State University and the Mag Lab. And this work would not be possible without all my collaborators. I have many of them to mention and name, which I will do during the course of the talk. And hopefully, during the course of my talk, it will become clear what each of these images corresponds to and what my title really is all about. Okay, so just bear with me, and hopefully by the end of the talk, it'll become all clear. So first of all, I'd like to thank Adrian and the other organizers for organizing this seminar series. I think it's a great way of connecting researchers across all sorts of subfields. And this is from your website. It says subfields, which I'm taking as an indication that I need to have some introduction where I get everyone on the same page because they may not be speaking the same language that I'll be using. So I'm going to spend a little bit time on the introduction and to motivate what are the kinds of physics problems my group is interested in. And really, the spirit of what we do is essentially everything from toy models, which are extremely, extremely useful for giving us insights. Now, there are phases of matter I'll be talking about, which just emerged primarily from toy models first before we started looking for them in real materials. But then there is this other school of thought, which is what I call the Walter Kuhn school of thought, which is that density functional theory and ab initio approaches have been tremendously successful. And so the question is, can we bridge these two worlds? And we don't really need to choose between them. There's merits in each one of them, and maybe we can leverage that to make progress. So part one is going to be more about, okay, hey, we're going to look at a lot of experiments. We're going to write down some model Hamiltonians, try to get some effective model Hamiltonians that do a good job at describing, the experiments and hence give us some validation, or we might be looking at a new phase of matter. And in part two, I'm going to say, what if we didn't have this experiment to look at? Is there some, this is a theorist's dream. Can I just look at this position of these atoms and try to figure out everything about what the system is doing? So that's the sort of perspectives that you're going to see in today's talk. And as I said earlier, feel free to interrupt me at any stage. Okay, so what are some problems that condensed matter folks are working on? Well, there's a lot going on, but just to summarize some of the important things that have gone on and are going on, you would have certainly heard of twisted bilayer graphene and other moire or superlattice systems. There's all sorts of connections and similarities with physics, even though the microscopic details are, of course, very, very different from the high temperature superconducting cuprates. And the nice thing is that these are 2D systems, which is great. You can twist these all sorts of 2D materials relative to one another, or you can have lattice mismatch as you have in transition metal dichalcogenide systems. And so this has really opened up a new field of twistronics and moire systems. But if you see a little carefully, you'll see that the underlying lattice that we're showing here is not a square lattice like you have in the cuprates. You have a triangular lattice. So already you see that frustration, things where the lattice geometry offers a new angle to, in addition to quantum mechanics, is going to be important. So just coming back to the other thread of my talk, so I'll be talking about some of the quantum systems that we've been studying. And the other thread of my talk is to say, okay, so, why don't you just put it on a computer and solve everything, and, we're all done. And that's easier said than done. I mean, these are basically two schools of thought that I mentioned briefly, where you say, yeah, okay, on the left-hand side, I say I make no approximations. I just write down Coulomb Hamiltonian with, electron-electron interactions and kinetic energy. And on the right, I make this approximation saying that, oh, I only care about the valence electrons. I just care about those electrons that are close to my Fermi level, or those that are participating in the low energy physics. And both have their advantages and limitations, as I mentioned earlier. But the key thing I also want to emphasize during the course of this talk is that it is not as trivial as you might think it is. Right? So there is a lot of effort in trying to ask what model Hamiltonian, emerges from this, ab initio Hamiltonian. And this is a very big field that lots of people have worked on. I would say one of the early pioneers in this direction was Ole Anderson. And some of his techniques are actually widely used in the density functional theory community. But when it comes to strongly correlated matter, I would say this is a fairly open problem, and I will introduce you a little later in the talk to the research that is going on, both in my group and elsewhere, and what sort of puzzles have arisen from this kind of trying to bridge these two worlds and to come up with this mapping. Okay, so first part first, we'll discuss what are the interesting physics problems that my group and others are working on. So my group focuses a lot on frustrated magnets. Already gave you a little bit of motivation for why frustration is important. Well, it's not a square lattice anymore. You take these two layers of graphene, or you take these mismatched transition metal dichalcogenide systems, and you already see that there's an emergent triangular lattice. But triangular lattices exist also in nature in all sorts of different guises. So there was a material that was studied a few years ago, which was ytterbium-based. There's the Kagome geometry, which is sort of close to our heart, I would say. And Herbert smithite, which is a green mineral and whose crystals are now grown in labs, is one such compound that has the same elements actually as the cuprates. I mean, it has copper and oxygen, but the copper is in a Kagome network, which is a lattice of corner-sharing triangles, and it's not in a square network. And spin half Kagome is not the only interesting thing out there. Just want to clarify. We've also worked on some spin 1 versions of these compounds, which also exist. In fact, they've all existed for a long time in the chemistry community, just that no one thought of, oh, what's the magnetism of these things? So as physicists, I think we can learn a lot from what already exists in chemistry and see if there's some interesting physics to do with it. So that was certainly the spirit of some spin 1 compounds that we worked on. And then more recently, and this is something I'll highlight in the talk a little bit as we go along, is that 2D is not the only interesting thing, although it's very, very interesting. 3 dimensions, high amount of frustration, as you see in pyrochlores. You might say, oh, pyrochlore, it has coordination 6, so, all sorts of mean field theory should work. Well, that's not the case. Even though it's a lattice with a very high coordination number, the high amount of frustration actually gives rise to all sorts of exotic phases. So there's all sorts of materials out there, all sorts of lattices out there, and at some point we have to say, okay, what are we looking for? This is just a slide to say that this is not the only kind of interesting thing that is going on in magnetism. Some of you may know that there was a Nobel Prize given for spin glasses, which I would say is one of the first examples of a frustrated system, but it's also disordered. And the systems I would be focusing on are, disorder-free. So we just ask, okay, what is the clean system? What are its properties? What are its ground states? What are its dynamics? What does its dynamics look like? And then there's a other kind of frustration where the lattice doesn't look frustrated. It's a honeycomb lattice, but the frustration is in the interactions. And this is itself a very, very big field of research, which is people studying all sorts of Kitaev materials inspired by Kitaev's exact solution, which actually gives rise to a spin liquid. And my friend Pontus Laurel is in the audience and has done some very nice work in this direction as well. So let's get back to the frustration of the kind that I was talking about, the kind I was mentioning, which is geometrical frustration, where the lattice itself, has some geometrical motifs that make it difficult to, solve the quantum problem. Before we solve the quantum problem, let's talk about the classical problem. Say, oh, classical mechanics is simple. I did it a long time ago. Well, let's just wait a little bit in that regard. So you take spins that are Heisenberg-like. They don't have to be Ising-like. Ising frustration, where people give this example of 2 up, 1 down. Yes, sure. It gives rise to a lot of exponentially many states on the triangular lattice. But let's say you allow these spins to rotate freely, right? As in the Heisenberg case, they're 3-dimensional spins. You say, I'll forget quantum mechanics for a moment. I'll say, okay, what sort of ground state exists for just spins on a Kagome lattice, which actually satisfy, which want to minimize this energy functional, which is SI dot Sj, which can be written as a sum of 3 spins. So Si plus Sj plus Sk square up to a constant. And you say, okay, I just want the sum of 3 spins to be 0. Sure, simple. Which is what I indicate with the 3 arrows or with the 3 colors. So you can think of every arrow being associated with a color, 1 red, 1 blue, 1 green. And it turns out that this can be done in many, many ways. It can be done in exponentially many ways. So let's see why that is true. So if you were on the triangular lattice, actually, it can be done only in a couple of unique ways. But here, because you have a Kagome lattice, you're going to see why the number is exponential. So of course, if you looked at the triangular Ising case, then that would be exponential. But if you allowed the spins to freely rotate, then up to some rotational symmetry, up to some rotations, it actually would be a unique case. But on the Kagome, it's far more interesting, I would say, because now you can say, oh, let's put every triangle to be 1 red, 1 blue, 1 green, or every up triangle to be 1 red, 1 blue, 1 green. I don't know if you can see my mouse. I hope you can. But you see that every up triangle has the same orientation and red, blue, and green, red, blue, and green, red, blue, and green. And that's associated with these 3 arrows. There is actually a very, very distinct configuration, which might superficially look like the same, but it's not. Because if you look carefully, here the up triangles have a red, blue, green. Then the next up triangle has a green, red, blue, and then a blue, green, red, and so on. Okay, so this one, basically all the up triangles have the same orientation of red, blue, and green. But on the other one, it doesn't. It does repeat, but it has an enlarged unit cell. So you can see that you go from this red, blue, green to this red, blue, green. You got to skip, some unit cells. And so there's an enlarged unit cell here. And what I'm indicating here is the 2 color loops, right? So I'm indicating that there's red, blue, red, blue, red, blue here, right? These are 2 color loops. And if I switch red with blue, blue with red, red with blue, blue with red, I'm still going to be in the low energy manifold. I'm still going to be in the ground state manifold because these are shielded by the greens, right? So I change red to blue, blue to red, red to blue, blue to red. And because I'm surrounded by greens, I still have a classical low energy state. And here I can do the same thing. I have identified 2 color loops, which are hexagons. I change red to blue, blue to red, red to blue, blue to red. Well, I'm again surrounded by greens. So every triangle is still happy, still satisfies the minimum energy condition, and you're still in the ground state manifold. Turns out that an analogous calculation for how many states there are, you can do it numerically, but if you want to do analytically, you can actually go to the honeycomb lattice, which is the dual of the Kagome lattice. And then instead of coloring the vertices of the honeycomb lattice, you color the links of the honeycomb lattice. And that was done by Baxter long ago. But the idea is already apparent from these figures, is that you can do these local rotations, or you can do these, you can take these winding loops and you can change blue to red and red to blue, and you get another solution for free. So it's really, really a very complex landscape where you have many, many low energy classical solutions. And then you might say, oh, quantum mechanics, will, typically favor some sort of, by order, by disorder, might favor one of these classical solutions. But it turns out that quantum mechanics can do other funny things, like take superposition of many of these competing states. And so this is the lesson that we've learned from 30 years. I'm just summarizing 30 years on one slide, so I'm not going to be doing a service to everyone who worked on this problem. But you can see what energy scales are involved, because you have many, many classical solutions. Now you say, I want to do better than classical mechanics. I want to, get the quantum ground state of the system. And you can see that there are states that don't resemble any of these coloring states that I mentioned. And in fact, the states can look very different. So you can get a valence bond solid, which was an early candidate that was sort of studied by Marston and Zeng, which was revived by Senthil and Nikolic. And you can see that its energy per site is about 0.432 J. We're going to make sense of this number in a minute. And if you do a more sophisticated calculation, so there were these early mean field calculations and exact diagonalizations by Sachdev and Whitelser respectively. But if you do a more sophisticated calculation, you do a DMRG calculation, which allows you to go to larger system sizes. What I'm plotting on the y-axis, or what largely plotted on the y-axis, is the energy per site. And on the x-axis is 1 divided by the system size in some sense. So as you're going towards the left, you're actually going towards the thermodynamic limit. And you can see that the DMRG energies seem to be the lowest energy. We have a variational principle. So there seems to be the best possible energies that we can get. But what I want you to focus a little bit on is that these two states look very different. Right? One is a solid, which is indicated by the dashed red line, and these are the liquid-like states. So it's a difference between solid and liquid. And it's a very, very small energy scale. If I just eyeball it, it's about 0.002. Okay, or I can be a little bit more conservative. It's about 0.005 or so on. But multiplied by the scale of J, which is 200 Kelvin. So that's on the scale of 0.4 Kelvin. Let's be a little liberal. Let's say it's 1 Kelvin. That's still a small number. It's 0.1, 0.04 to 0.1 MeV per atom. And if you ask, okay, from first principles, we can do all of this. We can try to get a phase like this or study a phase like this from first principles. Well, the current best is at least an order of magnitude, or maybe even 2, worse than what you would need to resolve the energy difference between a solid and a liquid. And you can debate whether is it a quantum spin liquid of this type or that type. There's a lot of debate going on in the community. But just even in terms of energetics, it's a very small energy scale that we're looking at. So just to connect up my point a little bit, in the theory world, in the models world, we can actually go beyond the Heisenberg model. We can tune all our parameters and explore a phase space, which is the sort of thing that we did a few years ago. But the big question really in the field is, like, where is the real material on these type of phase diagrams? So yes, we do a good job with tensor networks, DMRG, including our chair is a world expert on that. You basically are still left with this question, because these energy scales are so competitive, that you always have this question of what am I looking at in an experiment, and what are the energy scales that I can get reliably. So the problem has now become a problem of getting the Hamiltonian to a certain accuracy, which is particularly important, not only from a quantitative point of view, but also from a qualitative point of view, because as I said, the difference could be between a liquid and a solid, and you don't know what you're looking at. I just wanted to add a little bit more, that I gave you the example of Kagome, but as I told you earlier, Kagome is not the only interesting frustrated magnetic system out there. There's 3D frustration, which people study as well. And there's a lot more work in Ising frustration, where you have hard axes for the Ising spins, where you have a 2 in, 2 out rule. And these particular systems are called spin ices. And a big push in the field has been to look for a quantum version of spin ice. So a quantum spin ice, just like we look for a quantum spin liquid on Kagome, we're now seeing, oh, is there some superposition of these 2 in, 2 out states? Because again, there are exponentially many of them. Turns out that there's a Pauling entropy associated with them. And it's not just some term. Actually, you can do specific heat measurements of the type that Ramirez and Bob Kaba and others did in 1999. And you can actually ask, from the specific heat, I can get the entropy, integrating out this C by T dt and so on, can get the entropy. And I can see actually a very observable consequence of what is being not captured, what states are not being captured in the specific heat. And that has to do with the residual entropy associated with the high degeneracy of states. So this sort of effort in classical spin ices has existed for quite some time. But there is a push to look for a quantum spin liquid or quantum spin ice, which is a more sophisticated version of what Linus Pauling told us with regards to benzene, where you don't have one dimer covering, you don't have one singlet covering, but you can have a superposition of many singlet coverings, and that is sort of the idea that is attributed to Anderson. And we are basically trying to look for some of these phases, including quantum spin liquids, in real materials. So what do we need to do? Well, we cannot see the superposition in an experiment. We have to get some sort of indirect inference from experiment. And so one particular thing that we do, my group does, is that we basically look at neutron scattering experiments very carefully. So this is just a little bit of tutorial for those who may not be familiar with neutron scattering, is that, you have your magnetic material, your neutron comes in, exchanges angular momentum, flips a spin. And if it's a magnon, right? So if it's a very coherent quasi-particle that you've created, well, you'll see a very sharp dispersion between energy and momentum, right? So you can infer the momentum from the exchanged momentum. You can look at the momentum of the outgoing neutron and the momentum of the incoming neutron. And from that, you can infer Q, the momentum transfer, which is what is being plotted on the horizontal axis. In this particular compound, it was a copper sulfate crystal, which was essentially a Heisenberg model in one dimension, and was subjected to a high magnetic field. So basically, you realize a ferromagnet. And so if you just ignore this flat band, just for the sake of argument, just ignore that, then you actually see that E versus K is a sharp parabolic dispersion. But now if you have an antiferromagnet in one dimension, and we know that we cannot have true long-range order in one dimension, you see spin-ons, you see evidence of spin-ons, you see continuum of excitations on top of what would have been the spin waves, what would have been the linear spin waves, but they don't exist. The linear spin waves don't exist, but rather you get a continuum of excitations. So actually, there's a wealth of information stored in neutron scattering data, which is the sort of thing that we model, which is that you have 3 dimensions of momentum transfer, to be precise, and omega, which is energy, right? So you're looking at 3 dimensions of momentum and 1 dimension of energy. And for us theorists, it's basically just evaluation of some time-dependent matrix element. Now, this expression is actually done at 0 temperature, but you can also generalize this, with the Kubo formula for finite temperature. So this is the sort of thing that we want to calculate, and this is the sort of thing our host Adrian is well known for. In one dimension, he does a lot of TBD calculations, but actually there are alternatives to doing that in high dimensions, which is what we encountered, and I'll just briefly mention what we came up with as well. So great. So let's say somebody gave us a model Hamiltonian and somebody asked us, oh, hey, go and compute this. We at least have some tools at our disposal where we might even start to try to evaluate this. But then we can ask, what are the model Hamiltonians what do the model Hamiltonians look like, and do we agree on a universal set of parameters? And so, yeah, I have to thank my friend Pontus, who's in the audience, for compiling this. It's in a very, very nice paper. And this is done for yet another magnetic system. But actually, the story in spirit is very similar to the pyrochlore compounds. And you can see that Pontus basically very nicely compiled a whole list of models that people were studying. And you can see that there's predominantly the Heisenberg term and the Kitaev term and other, asymmetric terms as well, antisymmetric terms as well. But you can see that if I look at all these methods that people have done, including DFT, spin wave, magnetic specific heat, there seems to be a lot of disagreement, not only in the magnitude, but in some cases also the sign of the parameters. So you might think somebody should have figured this out for strongly correlated materials, that, how difficult can it be to get 2 or 3 parameters? But hopefully this kind of table gives you some perspective for why this is still a very, very challenging problem. Right? So in fact, we encountered this in the context of pyrochlore magnets as well. And that table was taken for a different magnetic system. But as I said, I focused mostly on pyrochlore systems. And a few years ago, 10 years ago or so, there was a lot of neutron scattering done on what is called ytterbium titanate. So ytterbium is a rare earth, this strong spin orbit coupling, and that's the magnetic ion that participates on the pyrochlore lattice. Turns out that when you have strong spin orbit coupling, you really cannot think in terms of Heisenberg physics. So you got to worry about anisotropic interactions. So you have anisotropic interactions because of pseudospin halves. You have data from neutron scattering, which is a lot of data actually, because you can look at all sorts of cross sections for Q and omega. You can also subject it to a magnetic field and do the neutron in a high magnetic field. So, well, yeah. So you have that knob as well. So you have a lot to look at to infer what the model Hamiltonian is, which is the sort of spirit of things that we and others in the community did. But it has taken a whole decade to converge on what is really happening, even though we were all looking at the same data or similar data. Maybe the purity of the crystals was slightly different, etc. But what started off as a quest for looking for a quantum spin ice and looking for an exotic phase of matter, actually the consensus seems to be that we're looking at a ferromagnet, which is very close to a phase boundary. So it was very difficult. So if you have a ferromagnet, but it's very close to the phase boundary, then you can say, oh, these spin waves will look highly, damped and highly renormalized, etc. So at that point, it could be very difficult to see, what's the difference between highly renormalized spin waves and spin-ons. But over time, I think, over all sorts of different measurements, including magnetization measurements, neutron scattering, specific heat, and so on, the emergent consensus has been that we, first of all, agree and converge on the parameters. Sure, that's one thing. And the second is we actually converge on what is the qualitative outcome of all of this, that, ytterbium titanate is close to some sort of phase boundary in this parameter space of model Hamiltonians, which is what made it very challenging. And the second thing is, that we can actually reasonably accurately, although our methodology in 3 dimensions is much cruder than what it is in 1 dimension, reasonably accurately understand what's going on in both zero and finite magnetic field. So we started to look for a quantum spin ice inspired by some previous work, but consensus seems to have been that it's not a quantum spin ice. So we were very interested yet in looking for quantum spin liquid spin ices in situations which maybe hadn't been seen earlier. So we were introduced to work by Bob Cava, and the neutron scattering was led by Kem Plum and Colin Broham. And what we saw is that in the specific heat, you do not see any sign of an ordering transition. So this is yet another pyrochlore, but now it's a spin 1 pyrochlore. It's a nickel-based pyrochlore. The previous one was a ytterbium-based pyrochlore. And so you might say, oh, spin one means largest spin, oh, which means, that largest approximation should work. It should basically order. But we didn't see any sign of magnetic ordering. And we dug up a lot of the theoretical literature and seemed to be all sorts of conflicting reports about, oh, whether you can have a spin liquid or not. But nevertheless, the experiment confirmed you're looking at nickel ions, so they are spin one effectively. You look at the specific heat, there's no sign of magnetic ordering, and these nickel ions live on a pyrochlore lattice. So what we did is we actually dug up what people had used for pseudospin half Hamiltonians. We dug up the literature for what sort of interactions parameterize, these spin orbit coupled compounds. So it turns out that in nickel, the spin orbit coupling is not so strong, but it's not zero. That turns out to be important. So it's essentially Heisenberg-like, but there are important non-Heisenberg terms which one has to account for, which this formalism accounts for perfectly. So we basically allowed for anisotropic non-Heisenberg terms in our model Hamiltonian, which I'm indicating with sublattice indices. So you have 4 sublattices on the pyrochlore lattice, 0, 1, 2, 3. And you can ask what is the coupling between a spin on sublattice I and sublattice J. So these matrices characterize that. You can see that there are 4 parameters. Turns out that there are 2 more parameters to do with the strength, with the coupling of the magnetic field. That's called the G tensor. So we fitted all of that to neutron scattering data. We basically, did all sorts of cost function analysis, etc. We also actually tried some density functional theory calculations, even though I said, oh, density functional theory is not so great for strongly correlated systems. And turns out that we could actually get the dominant Heisenberg J to at least within the right order of magnitude, but it was very difficult to get the subdominant scales, which are important for describing the neutron data. So let me just show you the outcome of all of this. So the thing is that we were able to get a model Hamiltonian from looking at experiments, from looking at neutron data, and also looking at specific heat and so on. And at the end of all of that, we were able to ask, okay, if this is our result, how well can we reproduce what's seen in the neutron scattering? So, when we saw these kit-type materials and the previous other pyrochlores, which, people were debating for a decade, we were not so optimistic that we would see a very good agreement, but actually we were able to describe many of the features that are seen in neutron scattering. So what am I showing here? I'm showing you, there are 3 dimensions of momentum, right? As I said, S of Q omega. So Q is 3-dimensional and omega is 1-dimensional. So I'm showing you, and we are very good at viewing things in 2 dimensions. So I'm showing you a 2-dimensional cross section, which is called the HHL plane. And then I'm showing you different cuts of energy. So I'm showing you an energy of 0.5 MeV, 2 MeV, 4 MeV, and 8 MeV. Turns out that the dominant scale of the interactions in that Hamiltonian that I just spoke about is the Heisenberg interaction, which turns out to be on a scale of 3 MeV. So 3 MeV is about 30 Kelvin, right? And so we were able to get features all the way from 0.5 MeV to 8 MeV. This panel on the left is what you see in neutron scattering. And this is what, if you look at the middle panel on the right, or second from last panel on the right, that's what we call Landau-Lifshitz dynamics. Some people call it molecular dynamics. And another ingredient, which is what is called a quantum classical correspondence, because we really just use classical evolution of spins in 3 dimensions. But we know that classical mechanics is not the full story. So we basically developed if you are interested in the details, you can read this paper, and I'm happy to chat about it. But with the moral of the story, or what we learned, is that once we got the right model Hamiltonian, once we got the right parameters, and there were about 5 or 6 of them, we can actually recover lots of things that the experiment is seeing, including this so-called bow tie feature, which has to do with this divergence-free condition. And in where this bow tie feature basically disappears, which is what happens at high energy. So we can get energy and momentum, we can get both energy and momentum features right, if one does a good job getting the model Hamiltonian right, which is what we invested a lot of time doing. Now, I don't want to give the impression that this is all perfect and there is nothing else to be done, because if you go down to very, very low energy, you start to see that there's problems with the molecular dynamics and the experiment. You're not going to have quantum mechanics to be perfect, or the quantum to classical correspondence to be perfect at all energy scales. But the key lesson that we learned basically from all of this is that if you look at intermediate energy scales, or another way to say it is that if you look at short time physics, actually a quantum classical correspondence gets a lot of features right. It turns out that we were not the only people to notice this. In the Kitaev model, where people can do all sorts of exact calculations, exact solutions, exact dynamics. Also, you can compare the classical and quantum dynamics, and you see at least qualitatively the features match a lot. So we basically had a lot of technology at the end of this project, and we encountered yet another pyrochlore. And this one is very far from a Heisenberg model, but the technology actually still applies. And this pyrochlore was discovered simultaneously by, or at least the neutron scattering was done by two groups at roughly the same time, by Peng-Ching Dai's group at Rice and Bruce Collin at McMaster. And once again, they saw in zero field, they saw absolutely no sign of any spin waves or anything of that sort. They just saw a continuum of excitations. So I'm just basically repeating the point, but the thing is that there was a lot of work done on what we call dipolar spin ices, where the spins are effectively like some effective spin half. They have dipolar character. They essentially act like Heisenberg-like spins, where they act like vector spins. But it turns out that in this particular compound, the chemistry on looking at the material really mattered. And you cannot really think of the spin as just having dipolar character. You have to think of it as having some octupolar character. And if that doesn't ring a bell, I'll just make that a little clear by discussing what the material's single ion physics looks like. So if you consider a single cerium ion, it has 4f1. So it has one unpaired electron in a 4f orbital. You do spin orbit coupling. So you just add one, which is 1/2 plus 3. So 3 plus 1/2 can give you 7/2, or it can also give you 5/2. And then you account for crystal field effects, and you see that the ground state doublet is something that has character, which has quantum numbers 5/2 and plus minus 3/2. Now, when we think of spin half physics, you go from plus half to minus half with a spin flip, right? But if I want to go from plus 3/2 to minus 3/2, well, I cannot just do a single flip of J, right? And just single J plus and J minus is not going to work. Which means to go from plus 3/2 to minus 3/2, I need 3 units of angular momentum. And that's where the octupolar character comes in. So you still have a doublet. You still have two states, much like a spin half system, where you have up and down. But now the way you connect up to down cannot just involve a J plus and J minus. You got to worry about J plus cube or J minus cube. And this was done with, this kind of project was primarily spearheaded by my postdoc, Anish Bhardwaj, and we collaborated with Andrei Nevedomsky at Rice, Anyan at Rice, Xu Zhang, who is now at Max Planck, and Roderick Meusner, also at Max Planck in Germany. So the upshot of all of this is that we had to look at the material Hamiltonian fairly carefully. We had to look for all symmetry allowed terms, which were actually very different from the dipolar case, which is also something that we had studied. We had to account for a funny Zeeman term. And you might say, oh, the Zeeman term is just H dot S, because that's what I learned in quantum mechanics 101. Well, the thing is that now you're working with a projected model. You're working with the effective low energy model. And so you're just mapping it to a pseudospin hub problem. And so, you will have a magnetic field term that looks like Sx is coupling to Hz, and this XYZ are in the local basis. It's a subtlety that I glossed over. And we had to account also for some next nearest neighbor interactions, right? So just doing all of this actually took quite a bit of time, but Anish was quite persistent. And what we were able to do is we were again able to take existing specific heat data. Sure, we cannot get very low temperature data very accurately because our quantum methods are limited. People are doing mostly numerical link cluster expansions, but we were doing finite temperature Langshos. So, you may say it's Langshos, but it's still, you have to do it many, many times to find the optimal parameters. And so that's what we did. We were able to get reasonable agreement with specific heat data with finite temperature Langshos. This is again magnetization data. So, you apply a magnetic field and you measure the magnetization in the same direction as the applied field. So this is an applied field of 111, which is the global 111 direction. And so we did all of this. And I just want to highlight a little bit of what we can study is that the end result of all of this is that we were able to get very good agreement between our neutron scattering signal and both the groups that had studied this, right? So, I mean, okay, there could be some quantitative differences, but the end result was that, a lot of the features that were seen in the neutron scattering data in the experiment and now in the theory, match reasonably well. So this is a powder average sample of Golin, and this is like a crystal of Pengcheng dye, and we can see very, very good agreement. But we had to do a very, very diligent job getting the Hamiltonian parameters right. So I think I'm a little bit out of time. I mean, I have 15 minutes, but I want to go to the next part of the talk. And I just want to say that we've also continued some of this onto different compounds, which is not, it's still cerium based, but the other ion is not zirconium, it's hafnium. So we've been continuing that with some groups in France. Turns out that the neutron resolution at PSI in Switzerland is a little better, so we can check our theories a little better, and that's also something that we've done. But I wanted to get to that, and I think I have 15 minutes, if I'm not mistaken, Adrian. And so, yeah, is that okay if I take 15 minutes? Yeah.
Yes, absolutely. Go ahead.
Yeah, I see that there are no questions, but it's okay. If there are any questions, feel free to interrupt at any time. But all of this basically relied on talking to experimentalists, understanding the details of what was going on, etc., etc. But we are theorists, and we have this grand dream, right? Every day I get up, I'm like, can I answer this question without talking to a single experimentalist? And I don't know, maybe my dream will remain a dream. But so the question really is electronic structure as we know it now, is it super accurate to help us with the problems that we were studying with all these pyrochlores, or what other people have done for Kitaev, etc. It turns out that the energy scales are very small. I don't know about the future, but currently the best ab initio techniques are about 0.1 MeV per atom. And then you can ask, okay, maybe I cannot get the exact ground state on the exact eigenstates and exact solution to this problem. But can I learn something from approximate wave functions? What if I write down a Slater-Jastrow wave function? Or what if I write down, some sort of matrix product state, which is maybe not exact, because there's limitations of bond dimension, etc. But can I learn something about what this low energy effective Hamiltonian is all about? Right? What are the important degrees of freedom, that are guiding the low energy physics? And this is actually a universal problem which keeps coming up in all sorts of disciplines. It's, I don't think, only constrained to strongly correlated physics. I think it's a universal question. But coming to like chemistry and strongly correlated physics, I just borrowed this notation from some of our chemistry friends. A physicist would say, oh, these states, these bands are unoccupied, but chemists would say, oh, those orbitals are virtual. Essentially the same language. I mean, essentially the same concept, just a different language. And the key idea is that there's a lot of dead weight in Hilbert space. There's a lot of virtual orbitals, or there's a lot of unoccupied states, and there's a lot of core electrons. I haven't shown all the electrons, which are closely tied to the nucleus. Those are not important in the low energy physics. So the idea is, how do I, if I know the full if I know the full Hamiltonian here, how do I get an effective Hamiltonian, right? So the key idea is there's a lot of dead weight in Hilbert space. And this sounds eerily familiar, right? Where have we encountered similar needs before? Where have we seen compressing vast amounts of information is required? Well, we know a lot about image compression now. And, Ingrid Dobitsch was actually awarded a Wolf Prize for this. And here I've just taken Leonardo da Vinci's most famous painting and completely butchered it because I saved it in a terrible resolution. But the thing is that if I improve the resolution a little bit, you can already make out that I'm looking at the Mona Lisa. And this is actually true of everything that is around us, right? So I just took this image today morning from Google Earth. And this is actually me sitting in the Keene building. And it doesn't, in the building at FSU, it doesn't matter that I'm sitting here and giving a talk and waving my hands because, the coarse-grained description is what is relevant. And this is also the basis of DMRG, tensor networks, neural networks. But remember that the object being compactified and compressed there is the wave function, is the many-body wave function. Whereas what we need to do is we need to compress the Hamiltonian, right? So we have many bands, or we have many virtual orbitals, we have these core orbitals, etc. We need to compress and ask what are the relevant degrees of freedom. And we need some diagnostic for figuring out, oh, is this a bad approximation or good approximation? We need both of that. I mean, we have that in the context of DMRG, right? We have a bond dimension which tells us, oh, you're getting better, you're getting worse. So we need some sort of knob in that direction as well. So just a quick summary of what is done in the state of the art. You might infer that, somebody figured this out and it's all solved. And turns out that what is done in the density functional theory community is that you typically look at the bands near the Fermi level and you Warnerize it. So you construct Warnier functions. And this is great for getting, all sorts of hopping matrix elements, etc. But for the Hubbard interactions, you need to do some post-DFT method. You need to assume some sort of screening model. So there's a whole, there's a whole community that does that. I'm not going to be doing justice to any of the work in this particular talk. But there are already some indications that there's going to be some problems because DFT does account for some interactions at the mean field level. So you've got to undo those interactions, and it's called double counting because you've got to undo what the Coulomb interaction did. And more recently, the group of Honerkamp and Werner and others actually revisited an approximation that is used routinely in chemistry and DFT, mostly in the DFT community, and basically said that this is actually very, very limited. So they actually took some more systematic systems where they could essentially solve exactly with quantum Monte Carlo. They considered some 3-band Hubbard models and so on. They basically showed that what people were routinely using for material science is actually very limited, which is where we enter the story, right? Or roughly where we enter the story, which is that we live in a democracy. So why should we treat kinetic and potential parts of the Hamiltonian differently? And maybe for weakly correlated system, it's okay. There's no democracy. The potential, the interaction terms are less important. But in what we are, in the strongly correlated things that we study, I mean, we got to restore that democracy, or at least that's just my personal opinion. And why not use information from wave functions, which don't really care about, oh, is this from kinetic or potential? And why not just use many body wave functions? And we want a method to have internal consistency checks, and we also need to think of a model as some sort of auxiliary system. Because look, if I take lanthanum cuprate and I just worry about just the dx square minus y square of copper, well, okay, I've ignored all the other electrons associated with the oxygens and lanthanum and so on. So I really cannot match say I match eigenstate of my model system to an eigenstate of the ab initio system. Well, that's not the right way to think about it, because the electron number is different. So what you really want to match is not eigenstates. You want to match properties of this eigenstate. You want to match some sort of correlation functions, or our chemistry colleagues would say reduced density matrices. And the simple criterion we used in what I'm going to discuss very briefly, because I have only 10 minutes, is that we want the one body density matrix and the two body density matrix. Physicists would say one body Green's function and two body Green's function to match. And that is the basis of our early work in this direction, which I'll be happy to discuss at some point if you're interested. So let me get to the key idea, which is that imagine I want an effective Hamiltonian, and imagine I have a good one particle basis. Let's say I constructed the Warnier functions, and I can tell you, okay, hey, these are the important localized orbitals that you should put into your model Hamiltonian. And maybe the method will say, oh, actually, you were wrong. You got to do better than this. But let's imagine that you've done that step. Now, you might say, oh, I need an exact eigenstate to do anything, to compare a model to the ab initio world. And the answer is no, because if you take expectation values on the left-hand side of this equation and the right-hand side of this equation, what have you learned? You have learned that the average energy or the expectation value of the Hamiltonian, whether you take it in the model system or whether you take it in the ab initio system, has to be the same. We're demanding that the one body correlation functions and the two body correlation functions have to be the same. You could say, oh, when you project the model Hamiltonian, you're not restricted to two body Hamiltonians. Maybe you have higher body terms. And that is certainly something that you can put into the formalism. But for the sake of argument, just say that we truncate this expansion. We don't put the higher body terms. Let's leave it at that. Then really the problem of downfolding is basically a linear algebra problem, because you can do this for many low energy states in the low energy manifold that you're interested in. And you can say, I'm going to make a vector out of all the energies that I encountered from my ab initio calculation. And these are my unknown parameters. And these are my matrix of density matrices. Right? So I basically just took this equation. I accounted also for a constant shift term, because I have a lot of core orbitals, which are also contributing essentially a constant shift, because the low energy physics, I don't see any excitation of a core, or I don't see the core electrons close to the nucleus pop up in low energy physics. And so I basically have, I need to make a database of wave functions. How to do that is a challenge, but let's say I made that. I need a good single particle basis. How do I do that? Again, a little bit of a challenge, but we are reasonably okay at constructing Warnier functions, etc. And so then we are left with the problem of determining the parameters, which can be extracted from you can do a least square minimization problem, and you can extract the best parameters that satisfy this relationship, because you might have some internal inconsistency because you truncated this series and so on. Right? You might not have a perfect match because you didn't get all the terms right, but within your parameterization, you can get the best model Hamiltonian. Let me just show you how this works. So here I'm looking at different density matrices. I've summed over some of the ones that are related by symmetry. And if the energy is changing a lot with a particular density matrix element, well, then it's likely to be important in the low energy physics. But if there is a density matrix element, or there's a correlation function that doesn't essentially change in the low energy physics, well, then you might as well drop that parameter out. And it's maybe not going to contribute as much in the low energy physics, or maybe it's subleading important in the low energy physics. Right? So you can basically do diagnosis of this type to maybe filter out which parameters you want to keep and which you don't. And as I said, to get the Warnier functions, you can basically do a Warnier construction on top of something that a DFT code might give you, which are typically plane waves or the cone sham like orbitals. So I'm trivializing this a little bit, but actually important. Getting the Warnier functions is sometimes also very, very difficult. But let's say I have taken this particular basis, which is what we did for the hydrogen chain, which are also some other groups have been working on. So this is what the Warnier functions would look like at the bottom, and what looks at the top, what is at the top is what the delocalized, the plane waves would look like. You can do this also for a toy model. You say, okay, I don't want to touch that ab initio software right now. I want to understand it for something where I have perfect control of everything. Well, you can take a 3-band Hubbard model where you have copper and oxygen. And you can ask, how do I downfold a 3-band Hubbard model to a 1-band Hubbard model? So now remember that this 1-band Hubbard model, the single orbital, is going to be some linear combination of all the other orbitals that are involved, right? Because now you have one copper and you have many surrounding, you have 4 surrounding oxygens for it. So you basically need to write down a Warnier function for what one of these green orbitals would look like. And then you pose the question, I have this new single particle degree of freedom, which is what I'll call D dagger, and I have the original degree of freedom, which is C dagger. This Warnier function basically relates my D dagger to C dagger, right, via some linear transformation. Once I have that, I can ask what is the best 1-band Hubbard model that describes my data from my 3-band Hubbard model. And so this is something that we did. And I just want to highlight that this kind of thing actually has some predictive power, because you can learn the effective Hamiltonian from some small scale calculation. And you say, okay, I'll make a list of T and U divided by T and so on after I have learned the 1-band Hubbard model. And I can then check what is its predictive power? How well can I get energies in the 3-band Hubbard model? So I just want to emphasize that there's a whole order of magnitude reduction in scale of effort, because if you do the Langshows for 3-band Hubbard model, you need 112 million basis states, but for just 1-band Hubbard model, you just have 4,900. So it's greatly reduced. The complexity is greatly reduced if you can do this downfolding. I think in the interest of time, I'll just skip and say that we actually also did ab initio calculations and not just toy models. So here I'm showing you the example of a benzene molecule. And we use something called ab initio quantum Monte Carlo, which was spearheaded by David Seppeli at Urbana-Champaign. And once again, we know, or we've learned, or we've seen somewhere in the literature that the benzene molecule can be thought of as a Parisier-Popel-Parr Hamiltonian, or the physicists would just call it the Hubbard Hamiltonian. And once again, we can diagnose by looking at these density matrices what sort of states can be captured in a downfolding. So if I take that these are my Warnier functions that I need to keep into my downfolding, and I see that there are electrons that are leaking out of the space, well, that's where I know that I've encountered some limitation of downfolding. That means I cannot capture everything in the Hilbert space by just taking the low energy component of the Hilbert space. So these are some diagnostics that very naturally emerge from our wave function way of thinking about it, because you can see, is the weight on these density matrices summing up to 6 electrons? And if you see that the sum of 4.88 plus 0.02 is not 6, well, then there's a problem. In other cases, also, it doesn't perfectly match up to 6. So that means there's some coupling. It's not perfectly decoupled, the high energy part of the space and the low energy part of the space, but it's reasonable. It's closer to 6 than what this red value is. So these are the sort of diagnostics that our method can give. You can basically say, okay, how well does a Hubbard model capture benzene? And this is a whole 2 electron volts off. What I'm showing here is the fitted energy versus the VMC energy. VMC is just variational Monte Carlo. It's as I said, we use the ab initio quantum Monte Carlo software, it's very difficult for it to get exact eigenstates, but none of these are exact eigenstates. But they're just using this relationship between the ab initio density matrices and the model density matrices. And as we put more parameters, no surprise, we can actually get a much better agreement. So in the interest of time, I'll just skip and just say that there are other problems that we've been working on. Overall, I would say it's a very much an ongoing endeavor. It's not like, I just throw in a few buttons and it's all solved. It's very much an ongoing endeavor. There are other groups, including Adrian Faguin's group working on this, Steve White's group working on it, and some people are trying to do some quantum enhanced density matrix downfolding. This is from the archive just a few weeks ago, so I need to look at it a little more carefully. But I think there are many parallel and complementary efforts by the community, and I think that's a good stopping point for me. And I think yeah, I should just say that both models and materials are important for the sort of things that we do. And I see, various future directions that can emerge out of both the directions that I spoke about a little bit. And I really thank you for your attention. And I'm sorry I went 1 minute over time. So thank you so much. Yes.
Thank you, Hitesh. I think I speak for everyone. This was a very nice talk. I open the session for questions now. If you're in the audience, please feel free to raise your hand or unmute yourself.
Yes.
I think you were very clear.
Okay, it was so clear that there are no questions.
But I got questions because I'm interested in the technical details, but I don't
Yes.
want to
Right.
overwhelm the audience with boring questions. But
Sure.
maybe I can briefly ask you one question real quick.
Yes, please go ahead.
When you say that you have to do this least squares fit with all the single particle, two particle Green's functions,
Yes.
you need many states, many eigenstates.
Yes.
So if you had the ground states, clearly, I mean, you only have one state, but what
Yes.
other states? So if you're doing like using some ab initio method,
Yes.
what other states do you have access
Yes.
to?
That is an excellent question, and I do not have an automated. I do not have an answer like, oh, you do this, and so it's unfortunately a little problem specific. But you can ask this question for any problem in some sense, which is that how would I get an excited state on top of a ground state? Let's say somebody gave me the ground state. Let's say I have a magnetic system and somebody gave me a ground state. Said, okay, what will I do to get an excited state? So there are a few strategies. So you can say, I'll take something like a single mode approximation, where I'll say I'll introduce a spin flip operator, and it has some coefficient in front of it, and I can optimize it. So I can take a wave function of that sort to try to get some guess for what the spin waves would be. The important thing I want to emphasize, and I'll make it a little bit more precise in a second, is that these are not eigenstates. I do not need eigenstates. I just need some wave functions which are snapshots of this, which are giving me some snapshot of this low energy manifold. So I need a many body wave function, of course, because I need to calculate an expectation value. Sure. But that many body wave function could be linear combination of the ground state and an excited state. It could be, right? I mean, it doesn't have to be, it doesn't have to be the ground state, which is actually very difficult to get to. So another way of saying it is the following. Let's say I know my landscape is a parabola. I cannot get to the bottom of the parabola, sure, but I can get to somewhere else in the parabola, right? I cannot get to the bottom because it's very difficult. I need a very large bond dimension, etc. But I can still learn about the curvature of the parabola and say, oh, actually, I'm fitting to a parabola because I have this higher energy information. So I just wanted to clarify you on that point that we are not using eigenstates, number one. But number two, you brought up an extremely important point. There are certain strategies that we have. So in the quantum Monte Carlo community, I would just like to emphasize what do we do? We basically consider different spin states. That means we try to put unequal number of ups and downs, right? So that is one strategy of generating more states. Another strategy for generating more states is that you can take what we call a Slater-Jastrow wave function, and we take expansion of the Slater determinant. So you take many Slater determinants, and you put a Jastrow because that's good at getting the correlation between electrons, right? But you can change the coefficients of these Slater determinants, and that's like you're kind of sampling the low energy manifold. So all I'm saying is You're taking many Slater determinants. So you take, let's say you have a reference Slater determinant, and you create some excited state on top of it, and you create yet another one on top of it, and so on. So that's called CI singles and doubles, right? You take CISD wave functions, and you can actually change the parameters in front of those Slater determinants and re-optimize the wave function with a Jastrow factor. And you know that you're going to get a different wave function, which is sampling your manifold. Now, it's possible that you get a lot of linearly dependent states, right? Which is also the truth for any sort of fitting method. You might not be efficiently sampling the manifold because your states are too dependent on one another. So those are some sort of checks that we can do, and actually the fitting procedure would actually reveal those as well. So these are just some strategies, Adrian. I'm not saying that this is a black box procedure that it works for everything, but this is something that is very much ongoing. Like, how can we push this towards automation? That's something that we're definitely thinking about and working on. But I don't know if I answered your question.
Yes, you did very clearly. Thank you.
Yeah. Okay.
We have a question from
Yeah.
Bob Markowitz.
Yeah.
Bob, please go ahead.
So do you see RVB states in benzene?
Do we see RVB states in benzene? To be completely honest, I haven't looked at I haven't looked at the dimer-like correlation functions. I mean, I have just looked at, so I have some backup slides. I just looked at density correlations, and I looked at some spin correlations, and I just use these states to determine my effective Hamiltonian for me. But and the effective Hamiltonian would just be that of a Hubbard for 6 sites. But I think the question you're asking is, can these ab initio methods capture something like a resonating valence bond state? So the important thing is that not all ab initio methods work in that basis. They don't work in this singlet basis. I mean, there are some methods that do work in that basis. We work in a Slater determinant basis. So you would need many Slater determinants to get that state exactly right. But this is something that we actually haven't carefully explored. Because we were not necessarily interested in the ground state. We were rather interested in learning the low energy effective Hamiltonian and the landscape in which this thing is living, right? So as I show here, the benzene molecule, you have actually 42 electrons, but we put a pseudo potential. So you actually have 30 electrons that we simulate, but the effective model has 6 electrons. And what we're showing is that we can actually get, if you compare the Hubbard model with experiment, or you compare our fitted PPP model with just from ab initio calculations, you can get a lot of the experimental eigenstates right. But I think your question is, what is the qualitative nature of the ground state, and is it exactly the same as that of the Hubbard model or the extended Hubbard model? And based off this argument, based off just energetics, I would say yes. I think it would be similar. Did I answer your question, Robert?
I think so, yes.
Okay.
All right. I've got, if no one's asking questions, I will ask another one.
Okay, sure.
In the case of the 3-band, I remember I asked you this before.
No problem.
But in the case of the 3-band Hubbard,
yes,
you can actually change delta, right? EP minus ED,
yes,
and go
yes,
from a regime where in Hubbard mode insulating regime or charge transfer insulator, negative charge transfer insulator. So as you move this parameter, the nature of your single band Hubbard orbitals will change. In one
absolutely,
case, or like
absolutely.
the Shanghai singlet, or in the other case would look something completely different, like
Right.
be more localized in the p orbitals, more localized in the d orbitals.
That's right.
So, have you played with this? And
So we have played a little bit with delta. I think I show it here. Well, this is delta 3 and 5. So not a whole big range of delta. It's still a small range. But just to connect up a little bit with what you are saying, I think that's an excellent question, number one. Number two is that all the transformations that we are using between the 3-band Hubbard model orbitals, which are basically, think of as the copper dx square minus y square and the O, px, and py, and the effective 1-band model we have, it's just a linear transformation, which means this D dagger, is related to the C daggers just by some coefficients, right? I mean, by some linear combination of the C daggers. Whereas to get Zhang-Rice, you would have to do some sort of many-body transformation, because in the Zhang-Rice, these C daggers are tied to, a couple of them are tied because you have
Right.
this, right? So you need a different kind of transformation, which is something that we've been wanting to do for a long time, but we haven't. But I think it's a great question. I mean, you can ask, is there some many-body transformation that you would have to do to get this effective degree of freedom? And right now, we've confined ourselves only to one-body transformations, which is what one-year functions do for you, right? One-year functions just say, oh, there's a one-body transformation between the delocalized bands or the delocalized orbitals and this very localized orbital. But something like the Zhang-Rice, I think is certainly worth looking at, and this is something that we need to do, but we haven't done it. I don't have a awesome answer for you right now. I just have an answer that is I think that's a very interesting direction where, if these degrees of freedom are many body, you could ask, okay, I don't want to go to super high body, but I could go to the next order and just ask. Now there are more parameters to optimize, because I got to worry about that transformation being coded up by many more transformation parameters. So that is something that is certainly worth doing. Well, in this particular exercise, we did not try that. Another thing that we did not do, which Steve and Scalapino and Jiang are telling us is important, is that there could be higher body terms. So there could be density assisted hopping terms as well. So you have a hopping, and it's based on what the third orbital is doing. And these are things that we did not keep in our very simple scheme. But this formally can be done in our downfolding procedure, right? I mean, you can formally just keep higher body terms as well. I mean, now you just put a different set of Green's functions here. So really, in some sense, this is a quantum mechanical version of what you would do with classical fitting, right? Classically, you would say, oh, let's take two spin up and take one spin up and one spin down, and let's look at the energy difference, and that gives us J. In quantum mechanics, one has to worry about expectation values, and that's what we formalized in this procedure. But
right.
Just to connect up with your point of Zhang-Rice, we haven't looked at many body transformations yet.
Mm-hmm. Thank you. That clarifies it. All right. If there are no other questions, we thank Hitesh one more time.
Thank you.
I applaud for everyone.
Okay, thank you. Nice of you. Yeah.
And I hope we see you again for the next Quantum Matter seminar. Thank you, Hitesh.
Okay, thank you. Have a good day. Thank you. Yeah.
Bye-bye.